Morning, guys. Today we start a new chapter, the chapter of power amplifiers. Look, we have completed enough of analysis of signal amplifiers, common emitter, common base, common collector, on based on BJT, and also based on FET, we have done common source, common gate, common drain, etc., etc. Now we come to a different category of amplifiers. This is a totally different category of amplifiers. They are called power amplifiers. We must first try to understand what is a power amplifier. That means these signal amplifiers that we have discussed so far, do they not deliver power? Of course, they deliver some power, some little bit of power. They are not classified as power amplifiers. Why? Here, you see the signal amplifiers, that means the amplifiers that we have already discussed, are that enhance the signal amplitude or signal voltage level, retaining the entire frequency domain signal characteristics. That means if you are if the input is maybe a vocal song of a famous artist, the output should be exactly representing the input, only a little bit louder. The entire characteristics of the music and sound must be retained. Then, what is power amplifier? Power amplifiers are designed to enhance signal power. It means a signal amplifier that you have in your mobile phone, you have to keep the mobile phone near to your ear so that you can listen to it. But that amplifier does not have enough power. So if the mobile is a little bit away from you, you cannot listen anything. These are the power amplifiers which enhance the signal power. Like you can give it to a sound box, you can uh, you can uh, you can deliver sound in a huge auditorium where you need signal power, but for which the signal characteristics may be sacrificed to some extent. That is the clue. A power amplifier when you design in order to deliver a huge power, maybe 1 kilowatt of power, sometimes it happens the signal characteristics is a little bit sacrificed. Then another may must understand, say an amplifier delivers sound power, but power cannot be created or energy cannot be created. Where does the amplifier gets the energy? Amplifier draws power from the DC source. Right? That means it could be a mobile battery, or it could be a huge AC to DC converter. If you are using a huge sound box or sound system, it draws power from the DC source and delivers it as a signal power to the load, maybe to the speaker or to the horn, mic, etc. So, where from the amplifier gets power? It gets power from the power source. Maybe you are plugging in the sound box to your domestic AC supply, where it is converted to DC for the amplifier. That is from where it receives the power or energy, and it delivers sound energy. In Power efficiency of a power amplifier, of any amplifier, is measured as the signal power delivered to the load speaker divided by the power drawn from the DC source. For example, maybe if you have a huge sound system which is delivering 1 kilowatt power, 1 kilowatt sound power, then maybe it is drawing 3 kilowatt AC or DC power from the power supply, right? That ratio is called the efficiency. Emitter signal amplifier. I've said that this is a signal amplifier, not a power amplifier. But then why we go back to this? Because power amplifier, principle of operation of a power amplifier, a little bit tricky to understand. And to understand that power amplifier operation, we need to first see how a signal amplifier works as a power amplifier, or what is the power performance of a signal amplifier. Because we know its principle of operation, we know its various equations, etc. So it is always easy to start from here. So let us consider a simple common emitter signal amplifier. Then, for the output signal current, this is the output signal current here and here. The current goes to parallel path, this RC and RL. For the output signal current, the impedance load is RC and RL in parallel. And often, and most cases, RL is much higher than RC. So net parallel combination can be considered to be RC for just approximate theoretical calculation and understanding the principle, right? So put for the signal current, put for the DC current is not RL. DC current does not flow through RL. DC current flows through only RC and RE. And signal current flows through RC and RL, right? So signal load is RC. Next, let us say RMS value of this signal current is IC. Then what is the signal power output to this load RC? Is I square R, that means IC square RL. And what is the current provided by the power supply VCC? This provides ICQ, that means current for biasing, as well as this signal current. Signal current also is drawn from VCC. So current provided by the power supply is IC plus ICQ. So what is the power delivered by the power supply is voltage multiplied by current, VCC multiplied by this. So this is the power delivered to the load, and this is the power drawn from the battery. Now, we shall now not go to detailed calculation that we will do in the next slide. Here, the conclusion is, I just wanted to show you what is signal power and what is power drawn from the power supply. In a signal amplifier like this, only a small part of power taken from the power supply, that means this power taken from the power supply, only a small part of this appears here. That we have not yet gone through the deductions and derivations, but that we shall do now, a few minutes later. But the conclusion I am telling you, this part is only a small part of this. It only appears, only a small part of the power appears at the output. Now we shall go into this. I shall go into how I made with this statement, right? For that, the power amplifiers, there are a few classes of power amplifiers. We go to that legend. Say this is the signal period. Signal or sound signal is always a complex signal, but for our mathematical simplicity, we have taken a simple sinusoidal signal. Say this is the signal period. And power amplifiers are classified according to the part of the signal period for which the amplifying transistor or the amplifying transistor conducts. Like Class A amplifier is the amplifying transistor conducts for the full period of the signal. That means when we shall discuss class A amplifier, we shall see the transistor conducts for the full period of the signal, full 360-degree or 2 pi period of the signal. Class B is when the amplifying transistor conducts for half of the period, maybe only positive half or maybe only negative half, only half of the period. Class AB is when the transistor conducts for more than half period but less than full period. So whole period is 360-degree, half period is 180-degree. So maybe it conducts for 270-degree or 200-degree. Then it is called class AB. And class C is when the amplifying transistor conducts even less than half of the period of the signal. That means half of the period is pi. So it conducts only even less than pi period. Now a question may come that if the amplifier does not conduct for the full period, then how will it the signal sound? It will, that we shall see later on, right? Are the classifications. Next slide. We go back to that point. Power performance of a simple common emitter amplifier that we are used to. This guy is by now our friend. We know him very well. And this is the load line, etc. Right? So we start from here. We shall see how this amplifier, our friend, good signal amplifier, we have even tested it by simulation, by software, how it works as a power amplifier. First point. Power is supplied by the DC power supply, that means VCC. Part of this power is delivered to the load RL and the remaining power is dissipated in RE and in the transistor. So in this path, there are three items. RE, where power is dissipated, RE becomes hot. RL also becomes hot, power is delivered here. And also transistor becomes hot because this power is the voltage across the collector emitter junction, collector emitter terminals, and the current passing through this current multiplied by this voltage is equal to the power dissipated in the transistor. If this and that power normally generates heat in this transistor. So we have made a statement that power delivered by the power supply has three components. One component is in the load, another component is in the RE, another component is in the transistor. Also, the power goes through these bias resistors, but these bias resistors R1, R2 are normally very high in comparison to RL and RE. As such, power loss in them is ignored. I mean, we do not ignore it forever, but if we consider them, then my deduction will become very clumsy. So for the sake of deduction, we ignore them. Then we start step by step. What is the power delivered to the load? The output for which we want an amplifier, right? Say, at any instant, signal current is IC equal to ICP cos omega t. ICP is the peak value of IC, right? So this is the signal current and peak value is from 0 to P. That is ICP cos omega t. Say this is a signal current. First, mind it, signal current is there over and above the DC quiescent current ICQ. But I am now talking about only the signal current, right? So then what is the AC power given to the load? PLAC is average of this. Average over one period, 1 by T, integration of 0 to T, I square, IC square RL, because power is I square R. right? And you have done this integration, I think maybe in your school even. This integration, it gives rise to RMS value, which is ICP. RMS value is ICP peak value by 2, and its square is ICP square by 2. So I have, for the sake of mathematics, I have shown you the integration, but power I could write is equal to ICP square by 2. That is the RMS square, because I have to do I square R, this RMS square multiplied by R. So ICP square by 2 RL. That is the power delivered to the load. So when is this power maximum? This power is maximum from this equation when ICP is maximum, right? What is ICP? That is this peak value, right? This peak value. And what is this peak value? Remember the biasing condition, load line of this load line intersects here at VCC divided by RL plus RE, right? And ICQ is half of the load line. So ICQ is VCC divided by 2RL plus RE. So ICP is VCC divided by 2RL plus RE. So this is the maximum value of signal. If you supply very low signal, it will be low. The maximum that you can supply is this value, right? So ICP, in place of ICP, I put this value. Then what is the maximum AC power delivered to the load? Is VCC square divided by 4 RL plus RE whole square. Then there was a 2 here, it becomes 8. And in the numerator, there is an RL here. So this is the maximum possible power which can be delivered by this amplifier. There is a limit, right? Now, this power, that means maximum possible power delivered, also can be maximized if I make REZ. That is why this emitter resistor will always have a bypass capacitor. It will have a bypass capacitor, and in that case, the maximum power deliverable to the load will be VCC square by 8 RL square multiplied by RL here. It will be VCC square by. Please remember this figure. This is the maximum power that this amplifier can deliver to the load. Right? Here, I think I should put a caution to you, because these are the theoretical values. When we shall do simulation test, we will not be able to get these high values, because, you know, you learned biasing. If your signal is peak to peak like this, then this region of the transistor output characteristics is nonlinear, and here also is nonlinear. The top and bottom regions are nonlinear. So actually we deliver signal less, and I should say much less than the maximum that is possible. That is, this maximum ICP we do not supply, right? If you try to do it, there will be nonlinearity in the output and there will be distortion in the sound output. Anyway, today we are in the theoretical study. The maximum power that can be delivered is VCC square by 8 RL. That means it depends upon the voltage here and the load resistance here. So this was power delivered to the load. A few steps we have to find out. One step is power delivered to the load. Next step we find out power drawn from the ports. How much power is drawn from here? That we name PCC. The current supplied by the power supply is ICQ plus that signal current ICP cos omega t. Signal current also has to come from the power supply. It cannot just fall from the sky. So this is the total current drawn from the power supply, right? What is the average power drawn from the power supply? Is voltage VCC multiplied by this total current, and that is integrated over a period of time and then averaged for a period of time like this, right? Then this is a theoretical representation, and I always think you should understand the theoretical representation properly without going by shortcut method. Now, shortcut method is integration of 0 to t of any cosine or sine function is 0. Integration and then its average is 0, right? So what we are left with is only VCC ICQ. So what is the PCC? Is VCC ICQ. So what is the power delivered by the battery? Is only the battery voltage, maybe 10 volt, 12 volt, multiplied by the bias current ICQ that you have decided during the time of biasing. Very surprisingly, the does not depend upon the signal amplitude. That means once you have designed the amplifier and switched it on, the power supply will keep on giving this power. You may not use the amplifier, maybe signal input is 0, but this much power will be consumed by from the battery. If you signal and listen to some sound, then also battery power is only this much. So battery power consumed does not depend upon the signal. And this is one reason why when you are not using an amplifier, you should keep it switched off. Don't keep it switched on. Because if you keep it switched on, this much of power is always consumed from your battery. Right? Next thing, what I find, this PCC is VCC into ICQ. VCC is this, and ICQ we have seen here is VCC by 2 multiplied by RL plus RE. So it is VCC square divided by 2 multiplied by RL plus RE. And if RE as an emitter bypass capacitor, then you ignore the RE, it becomes VCC square by 2 RL. So power drawn from the battery is VCC square by 2 RL. And just a few minutes back, we have seen what was the maximum AC power delivered was VCC square by 8 RL. And PCC is VCC square by 2 RL. So what do we find? Maximum AC power deliverable to the load is battery power consumed PCC by 4, right? That is a very, very poor situation. That means the maximum possible signal power that can be delivered to the load is only 25% of the DC power drawn from the power supply. That means if you have to deliver 1 watt sound power, then you need a 4 watt battery power supply. This is a poor performance. In fact, at the very beginning, I commented that these common emitter signal amplifiers are poor power amplifiers. This is one reason. It consumes 4 times the power supply from the battery than the sound power that it can deliver to the load. Next thing, of the transistor. Power dissipated in the transistor, PT, right? At any instant, the current through the transistor is IC and the voltage across the BJT is VC. Then, if that is so, then a Kirchhoff's voltage loop equation here is VC is equal to VCC minus ICRL. I have ignored ICRE. ICRE is very, very small. VCC minus ICRL. Also, we have seen earlier, this total current through the load is the quiescent current plus the signal current, where small IC is the signal current, right? Then, what is the power dissipated in the BJT? Volt multiplied by current. So, voltage VCE multiplied by IC and integrated and averaged, right? Now, VCE is VCC minus ICRL. So, VCC minus ICRL. This IC, for the timing, I keep it at IC. I do not split like this, right? So, this becomes integration average of VCC IC minus I minus IC square RL, right? Now, what is this? Average of VCC IC is the power drawn from the power supply, right? So the PT will be this I replace by PCC minus this term. And this term now IC I break into ICQ plus small IC, that is bias current plus signal current whole square. So this will be PCC comes here. And once again, this is ICQ square RL because ICQ is not time dependent. So ICQ square RL plus small IC part will be once again ICP square by 2 RL. These are the three parts. So power dissipated in the transistor as a heat is equal to power drawn from the battery minus DC power consumed by the load minus the AC power delivered to the load. This makes sense. That means how much power is consumed by the transistor or heat is power is dissipated in the transistor is power taken from the battery minus the power DC power consumed by the load minus the AC power delivered to the load. RE is totally ignored, right? So when is dissipated in the transistor maximum? Is when it is zero because there is a negative sign. This is very surprising. That means when signal is zero, then power dissipated in the transistor is maximum. That means if you have an audio amplifier, you have switched it on, but there is no signal given, you are not playing any music, then the transistor becomes hottest. You must remember this. If you are not giving any signal, switch off the system. Because switch on, no signal makes the transistors very hot because of this equation. And PT, the power in the transistor becomes maximum when this is zero, right? In that case, what is the maximum power? Is this PCC minus ICQ square RL. Now, value of PCC I put here. Value of PCC we have done in last page. This is square by 2 RL. ICQ also we have found out it is VCC by 2 RL. It was actually VCC by 2 RL plus RE, but RE we have ignored. If we do this calculation, it is VCC square by 4 RL. That means maximum heat power dissipated in the transistor is VCC square by 4 RL. So this was power dissipated as heat in the BJT. Next we go to, after we calculated what is the power dissipated in the transistor, how much power is delivered to the load, and how much power is drawn from the battery, then we come to some commercial terms. First term is efficiency. Efficiency is given by AC power delivered to the load divided by power drawn from the power supply, right? And efficiency, that means is PLAC by PCC. These are the equations PLAC and PCC we have found out earlier. This becomes like this. This is the efficiency. Now look at it. When is efficiency maximum? When ICP is maximum. That means when signal is maximum signal that you can give to the amplifier. F is maximum when ICP is maximum. And what is the maximum ICP? Is equal to ICQ. And maximum ICP is VCC square, VCC by 2RL. Already we have ignored. VCC by 2RL is 25%. That means efficiency, power efficiency of this amplifier is only 25%, nothing more. Maximum efficiency of a common emitter amplifier is only 25%. This is the curve. This is the it's a constant. It doesn't depend upon the signal. This is the ICP axis. This is the corrected signal current axis. Of course, this increases when your signal increases. As your signal increases or decreases, power taken from the battery is constant. That is why we say, elderly persons of your family say, if you are not listening to the music, switch off the system or switch off the radio. And also what we find, this is the power delivered to the load, PLAC. As the signal increases, the power delivered to the load increases. And this is the power dissipated in the transistor. So look at it. When the signal is zero, signal increases in this direction, then this is the power taken from the battery, and half of it is dissipated as a heat in the load. And as the signal increases, the output sound power increases, and at the same time, the power dissipated in the transistor decreases, right? So it is as if there is a trade-off of power between the output load and the transistor. And efficiency also increases as your signal increases. When your signal is maximum, efficiency is 25%, right? So these are the pictures of earlier slide that I have brought in here. There is another term used here in case of power amplifiers, that is figure of merit. What is figure of merit? Efficiency is AC power delivered to the load divided by power drawn from the power supply at different signal amplitude. Figure of merit is the maximum of them. The maximum power dissipated in the transistor here, the signal is zero. See, maximum power is dissipated in the transistor, this blue line when signal is zero, divided by maximum power delivered to the load. That means this is the maximum power delivered to the load when signal is maximum. The ratio of this value when the signal is zero divided by this AC power delivered to the load when signal is maximum is called a figure of merit. Now, why we need this figure? I'll explain. So figure of merit is the PT max, that means maximum power lost in the transistor, divided by maximum power deliverable to the load. This is 2. Ratio is 2. That means if the amplifier is supposed to deliver a 1 watt sound power, then the transistor must be of a 2 watt rating. Because this is how you decide which transistor to buy or which transistor to use. If your customer wants a sound power output of 1 watt, then you need to use a transistor of whose rating is at least 2 watt, right? That is the figure of merit. What we find in a conclusion, that this basic common emitter cashless signal amplifier is a very poor performer as a power amplifier because its maximum efficiency is only 25%. This is the efficiency scale, right? And maximum power which it can deliver to the music power that it can deliver is only one-fourth of the DC power it draws from the battery. Its transistor gets very heated when there is no signal. So for all these things, this common emitter amplifier is a very poor performer as a power amplifier. Now, in our next lesson, we shall learn actual power amplifiers. Then you may ask me, sir, why we did this? That means, why did we find the power efficiency of a common emitter amplifier? That is because, as I said also earlier, you are friendly with this amplifier. You know what is what. So these deductions were easy. I hope you could easily understand the deductions, how we calculated the AC power delivered, how we calculated power dissipation in the transistor, how we calculated the power drawn from the battery. It is all easy with the help of this circuit because you know this circuit. But as a conclusion, we find this is a hopeless power amplifier. In next day, we shall go for we shall go for actual power amplifiers, but that is next day only. Today we finish our lesson here.